polynomial algebra is the polynomial algebra in these coordinates. We put a state on this polynomial algebra, and the pair polynomial algebra and state will give us a Hilbert space, the cyclic space. This is a standard construction, a scalar product on this space, and a cyclic vector that we denote phi0. Once we, moreover, in addition to this, the scalar product gives us two important additions. The orthogonal gradation, which depends on phi. I don't write everything every time the dependence on phi, but phi, p is intrinsic, is algebraic. Pn depends on phi. And the quantum decomposition Now, from the quantum decomposition, we have deduced two types of commutation relation. One type we already met in one dimension, which is coming from gradation present. Many interesting things can be said about this commutation relation, but we have no time to discuss this part, so we jump to the second type of commutation relation, and they come from commutativity. Of the coordinates Ej. Ej, remember now, I fix a basis linear basis and I use often the notation identified. So these are notations. And the same thing for the cap operator. Same thing for cap operators. Now, the second type commutation relation, we deduce it, and they are essentially three. Minimal set is three. The creators commute, then there is the commutation relation related then there is the commutation relation similar to the type 1 commutation relation, but they are not. For example, the creation annihilation that appears on the right is not the adjoint of the creation annihilation that is on the right. And finally, is just to remember that they come from the fact that xj commutator xk is identically 0, and then you keep the elements with the same degree. So these are the new commutation relations. Now the statement of the problem. So in one dimension, we have seen that given the pair we associate to it two sequences with the properties that we said many times. They characterize the so-called principal Jacobi sequences. Okay, I don't repeat the fundamental properties. Now, they're written I wrote it in the summary of the notes, but to be quick, I will not repeat. What is the important point, you see, is that the alpha n have no relation among the alpha n. No relation between alpha n and omega n. And the fundamental problem that we want to answer is what is the multidimensional analog of these two sequences. So the problem is multidimensional analog of omega n alpha. To answer this problem, make it see in this way. To answer this problem, let us do some heuristic consideration, some inspired by the one-dimensional case. In the one-dimensional case, we know that A minus A daga is omega lambda plus 1. Okay? But since the omega n start from 1, because omega 0 is equal to 0, this is equivalent to give the omega n. Okay? Moreover, we have seen that A0 is alpha lambda. Lambda is the number operator, remember. And this is equivalent to say that A0 is equivalent to alpha n. Now, why the analog of omega n and alpha n is important? This is because of a lemma so the Jacobi relation goes from the pair algebra state to Jacobi sequences. The Favard lemma goes in the opposite direction. That is, given the double sequence, the two sequences, omega n and alpha n, you reconstruct the state, and we mentioned and we explicitly constructed, not only to reconstruct in abstract sense, but you give an explicit inductive construction to the state. Now, so this intuitive analogy suggests that an analog of the Favart lemma could be that, in some sense, the pair will allow to reconstruct the state. So this is our conjecture, which is inspired by the one-dimensional case. And the conjecture is correct, but there is an important but. The two properties, the no relations, become false. There are relations between a daga A, in fact, the spectrum of A minus, A plus, spectrum I say in a generalized sense. Let me not write spectrum, because it's not really precise. Between A daga, A minus, A plus, and A zero. And in fact, here we have A minus, A plus. We know that in the multidimensional case is a kernel. And A0 is a sequence of a final D operator. We are in dimension D. A0 is determined by D self-adjoint operators. Okay? There are there are relations between. So there are relations between, and there are and in the following I will use always this notation to simplify. That I use this notation to denote the restriction of, I wrote for A0, but I will use this notation also for A plus and A minus. So remember that alpha n, in the one-dimensional case, the gradation is one-dimensional. So the restriction of A0 on Pn is uniquely given by a real number, because A0 is Hermitian operator. Okay? But here, Pn obviously is not, the big point is not one-dimensional, and the point is that, however, the A0 not only is Hermitian, but is also gradation preserving. So this is a similarity, because the operator A0 is determined by a sequence of real numbers, each A0j will be determined by a sequence of Hermitian matrices, which is the analog of a real number. Okay? So this will be the difference. And now this will, what is the logic that will bring us to do this? The logic is that you first of all study the properties of these kernels. So we introduce the multidimensional analog of this kernel. In one dimension there is only one index. In multi-dimension there is a multi-index. So I will define an operator for each jk. This is a, now remember that a plus is degree plus 1, a minus is degree minus 1, so the product is degree 0. It means gradation preserved. So this preserves the gradation. This means that omega jk, omega tilde jk, is uniquely determined by a sequence of operator n jk, each of which is a matrix. Because it goes from Pn into itself. And Pn is finite dimension. Okay? Now, the specific, this kernel, I think I mentioned that it is completely positive definite. Did we introduce this notion completely in the last lecture or not?
You mentioned it.
Huh?
You just mentioned but not introduced.
It is, I mentioned, well, the complete positivity we will not use. So let us use only positivity. But we use Hermitianity, which is important. The positive definite kernel will be called Hermitian. And if the adjoint of gk is omega kj. And this you immediately see from here. Because if you take the adjoint from this, you switch the product and change plus into minus. Okay? So this is Hermitian. So we have some specific property of this product which restrict a little bit, because Hermitian scalar, for example, if when you have the, for us it will be very important, the real and the imaginary part of this kernel. So when we have the real part of omega jk, that will be 1/2 of omega jk plus omega jk star. See? But due to the Hermitianity, this is equal to omega to the 1/2 omega jk plus omega kj. And this is symmetric in aj. So what does it mean? So this is also equal omega kj. But this has an important implication, because the adjoint, if we take the real part of omega jk and we take the adjoint of this, you see, this is the real part. You take the adjoint, this will give me kj, and this is jk, so is itself is equal. So this is a symmetric operator, means that each element is Hermitian. This is the analogy. So we have a positive, roughly speaking, if you think that the analogy with matrices, this is a matrix whose coefficients are all real. And it is positive definite. So it is more, because there are many complex positive definite matrices. But here we have a positive definite, okay, with real coefficients.
So omega tilde is, you're using omega tilde there now. So here this one, omega.
This omega tilde and omega, they are same or?
What is
Sorry, I forgot to put the tilde everywhere. this tilde is an historical reason. This should be without from the logical point of view. But originally we called omega the kernel of the full scalar product on Pn. And so we had already used this letter. And so in the paper with the Ferroviendari we used this, but probably for a better analogy, in the future we will erase this tilde. So we have this problem.
Omega tilde, the whole thing is Hermitian.
The
Omega tilde is just Hermitian, like the indices JK.
yeah, omega tilde. Yes, this is an object very general and very important.
That is Hermitian.
There is a Hermitian. No,
So here you don't have.
This is the definition of positive definite Hermitian kernel. It's like a positive
Okay, it's
definite
correct.
function.
Correct.
Not all positive definite functions are Hermitian, because remember, there is always the point. I can add to a positive matrix, I can add an arbitrary skew symmetric matrix, and still it will be positive, because the positivity condition is only on the diagonal. You see? So not every positive definite kernel is Hermitian. This is true also in the scalar case. Not every positive definite matrix is Hermitian, because I can add arbitrary skew adjoint. Okay? So